All right, so I looked through the discussion and at some emails I got, and it looks to me like everybody's pretty good on the first few sections or the first couple of sections in this part of the course. But there were a few things that I thought I'd just share with you about matrix multiplication, maybe talk for just a second about that. And then the questions that I saw mostly are about block matrices and using that kind of technique to optimize, when you're actually multiplying matrices together, because that's computationally expensive. So those are the two things I want to talk about today. Some new matrix multiplication stuff and block matrices. So if anybody has questions about things other than that, yeah, okay. So other than that, please let me know. Go ahead and type in questions, and I'll try to make sure that we get to them. So yes, we will do another example of block matrix multiplication, definitely. Okay, all right. So let me just start with this other matrix stuff. So I think I mentioned in one of the videos that matrix multiplication is not commutative. And the example I used, so not commutative, the example I used was two matrices that actually were incompatible with multiplication in one direction, and you could find the product in the other direction. So if we have some matrix like x is 2, 3, 1, 7, minus 5, 0, and y is 1, 2, 1, 2, you can take the product of these two matrices, x times y, that exists, right? Because this is a 3 by 2, and this is a 2 by 2. So the product x times y exists, but y times x doesn't, right? So the product y times x doesn't. So this is an incompatible dimensions issue. But non-commutativity is it's not just about dimension incompatibility, right? So you can have matrices, square matrices, that you could multiply in both directions, but their products are not the same. So like, let's see, let's take this matrix A. I'm going to keep the examples kind of small with some exceptions with the block matrices, just because it gets like a lot to write. So let's take this matrix A, and then we can take B is 0, 4, minus 2, minus 1, and compute the product. So I think based on what I saw in the discussion that everybody's pretty comfortable with this, and I can take the product of these two matrices. So this is going to be 0, minus 4, and this is going to be, so 1, 2, and 4, 1. So we'll have 4 minus 2, that's 2. And this is going to be 0, minus 8, so that's going to be negative 8. And then we'll have negative 12 minus 4, so that's negative 16. All right, so that's A times B. That looks weird. And let's just take a quick look at B times A. So let's see, what's the product here? We can still compute the product because these are 2 by 2 matrices, so we can multiply them either way. But if we start multiplying, let's see, this is going to be 1 times 0, that's 0. Let's see, negative 2 plus 3, that is 1, and negative 2 minus 4, so that's negative 6. So these are definitely not equal, right? Again, so the point is it's not just about the incompatible dimensions, right? Which can happen, right? We see like these two x and y have incompatible dimensions, so you can't even take one of the two products. But even if the dimensions are compatible, you're not ever expecting this to be equal to this. So in general, AB doesn't equal BA. All right, so that's something I really want to highlight, because it's one of the first kinds of multiplications that people see that's not commutative. All right, so let me give you a second to think about if you have any questions about that. Can you guys mute whoever was laughing? I'm happy for you to laugh. That's totally fine, but maybe you could just mute. Okay, so no questions. About that then. So we can go ahead and go on. Let's see, what time is it? How come -6 in the last one? I got -8. Oh yeah, you're right, it is -8. Other questions? Okay, all right, so then let's go on. There are a couple of kinds of sort of fun kinds of matrices that do nifty things. So let's see. And being able to identify these and what they do can help you when you're trying to block matrices out for the purposes of optimization. So let's maybe, let's start with, well, okay, so there's two that you already know, right, from the videos and the reading and stuff, and those are identity matrices and the zero matrix. These are super special, right? They're extra important. They're the ones you learn on the first day. Right, and the identity matrix is called that because if you multiply a vector, or sorry, if you multiply a matrix by the identity matrix, you're not going to get a change, right? It's always going to be the same. But they work that way when they're square matrices. Zero matrix, all zeros. When you multiply by that, everything is zeros. So these are special matrices. They're special for multiplication. Okay, so let's see. Okay, so sometimes I have people ask me about non-square identity matrices, and you can sort of, well, you can do some things with non-square matrices that look a little bit like the identity matrix. So let's take an example. Let's see, how about this one? All right, so I want to take the product of this matrix with this matrix. So this is a square, this isn't a square matrix, so there's not like a matching size square identity matrix, but I just want to make something that's conformal with with this matrix for multiplication. So what is this? This is a 2 by 5. All right, so, and I guess you can see, like, see here, this kind of looks like a 2 by 2 identity matrix, right? But let's compute and see what happens when we start multiplying these two matrices out. So if I compute D times E, and I can do this, right? Because this is a 2 by 5 and E is a 5 by 2. I know that I'm going to end up with a 2 by 2 right? So the middle ones cancel out, and then we keep the edge ones. I know that I'm going to end up with a 2x2 product, right? So I have 4 slots to fill in. And if I look at what's going to go in the first slot, so first row, first column of E, this column is all zeros except the one at the top. So it's just going to have the same entry as that first entry in the D matrix. And if I work on this one, right, to get this entry, I'm going to use the first row of D and the second column of E, and that's got all zeros except for a single one as well, and that one is going to pick out the -5. And similarly, if you work through these last two, you'll see that this is going to pick out the 3 and the 8. So if we recognize like this kind of matrix E, and what it's going to do, right? This is going to exactly pick out, you know, when we multiply on the right by a matrix that looks like this, it's going to pick out the beginning entries of our matrix that we have on the left. So if you're trying to just pick some stuff out, this could be a completely inefficient way, you know, multiplying by matrices to pick out the top 2 rows of an array. But in any case, sometimes it's useful to know that these kind of things exist. Okay, so let me mention a couple of other kinds of matrices. So one I wanted to point out, and I talked about it a little bit just structurally, properties of diagonal matrices, but we didn't, at least I don't recall making a point of how they behave when you multiply by them. Let's see. So let's see. I want to use square matrices again. Maybe I'll call this one D for diagonal. Okay, so Pablo, are you talking about like using equals equals in code, right? Like in a program? And I don't know the answer to that. It might depend on what language you're working in. I'm trying to remember. I think MATLAB would say that they're not equal, and MATLAB was originally written in Fortran and is now in C++. So probably MATLAB and C++ and Fortran would say no, but I don't know about. Yeah, Cassie, I don't know. I would think they would say no, but if if whatever you're using, like if you have 2 things that are different sizes, if it automatically pads with zeros, then you know, then it might say yes. I can't imagine anything doing that, but I don't know every language, so I have to say I don't know. Maybe somebody else can think of an example where they would it would turn out to be true, like ED equals DE. Anyway, so let me go on with this example. It's a good question. All right, so this is a diagonal matrix because its only non-zero entries are on that diagonal. And so let's see what happens when we are multiplying matrices by a diagonal matrix. All right, so if I'm going to do D times A, this is 5, 0, 0, 2 times 3, 0, minus 5, 1. Let's see what happens when we multiply this out. So you can do it yourselves. You can just check my work. Please do, because obviously I make mistakes. So I get 15 here, 0 here. And then on this bottom one, I'm going to get 0, minus 10, and 2. Okay, so after multiplying this out and upon a little reflection, you might notice that this is 5 times 3, 0, right? We're just taking this number and doing like a scalar multiple of that top row. And this one is just 2 times the entries in here. So we're just basically taking that 5, 1, that minus 5, 1, and doing a scalar multiplication by 2, right? If you, like, again, motions of the multiplication, you'll see that that's always going to be the case. So if we multiply on the left by a diagonal matrix, the net effect is that we're just be multiplying the rows of the matrix by the corresponding diagonal entry. On the other hand, if you multiply, we know matrix multiplication isn't commutative. And so if we multiply on the left by a diagonal matrix, we're going to get scalar multiplication of the rows. If you multiply on the right, let's see what happens. So if I take A times D now instead of D times A, work it out. We're going to take 3, 0, multiply it by 5, 0. So we're going to get 15. And then here we're going to get 0, 0. That'll still be 0. And then for this one, we're going to get, let's see, negative 25, 0. So this is negative 25. And this will be 0, 2. Okay, so now in this case, what's happened is this column, what happens is we take kind of this column, the 3 and minus 5, and this thing is getting multiplied by 5. Right? And if we look at the other column, right, this column, whoops, this column is just getting multiplied by 2, right? It's those corresponding entries in the diagonal matrix. So when you multiply on the left, you're multiplying the rows of the matrix. And when you multiply on the right by a diagonal matrix, right? So we multiply on the right by a diagonal matrix, you're multiplying the columns by those corresponding diagonal entries. Okay, so I'll let you play around with that and take a minute and see if you have any questions. And then, let's see, how are we on time? Okay. And then I'll show you one more kind of matrix, and then we'll talk about block matrices. Any questions? Okay, so I want to show you one more kind of matrix, and these turn out to actually be super important in the stuff that we're going to talk about next week, which is this technique. Wait, let's see. Well, we'll see them again next week, but they'll be super important for the week after that, right? So about the unit we're going to do about Gauss-Jordan elimination. So let's see. These are called elementary matrices. Elementary matrices are comprised, well, the ones I want to show you right now are of one sort. They're comprised of all zeros and ones, and they differ by just one place from the identity matrix. So here's an example. Let's see. Let's do 1, 0, 0, 0, 0, 1, and 0, 1, 0. So if you look at this, you'll see that this is just like the identity matrix, except like if you took the bottom two rows and switched. So this is the same as I3 with the bottom two rows switched. Right, so let's see what happens if we multiply another matrix by this. This is, let me call this, I give it a name, we'll call it E1. All right, so let's take a matrix, say 2, 1. Oh, actually, I don't need to make up fancy numbers if I'm just doing this, a simple. All right, so here's a matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I'm gonna multiply this by E1, this isn't quite a diagonal matrix over here, so this is gonna do something different. But if you start multiplying out, I think you'll see what's gonna happen. So this is gonna end up being a 3 by 3 matrix. Right, so if we start multiplying, we'll get 1 times 1 plus 0 times 4 plus 0 times 7. So that just gives us a 1. And then we do the next two entries in this first row, we'll get 1 times 2 plus zeros, and then 1 times 3 plus zeros. So it's kind of like this is just picking out the first element of each row, each column of the other matrix, right? So we're keeping 1, 2, 3. Okay. Now here is where the magic happens. All right, so let's compute along this row of the product matrix. So the second row of the product matrix. We're going to use the second row of the first matrix over here, and then each of these columns in turn. So this will be 0 plus 0 plus 7, and then 0 plus 0 plus 8, and 0 plus 0 plus 9. So that's identical to the bottom row of our original matrix, but now that's the second row. And then working out the last row. So I should say first that this row right here is serving to kind of pick out these bottom entries and put them here in the middle of the matrix. And if we go through the last one, you can probably guess what's going to happen. This row is going to pick out the middle entries of each of these columns. So we'll end up with 4, 5, 6. So matrices like this, these are exactly just swapping rows. Sorry, guys, my son just walked in and he really wants to tell me something. I'm not sure what it is. What is it, sweetie? No. No. Go and talk to Grandma, please. Close the door. All right. Does anybody have any questions about math? Okay, so multiplying on the left by one of these identity matrices like this E1 over here is going to swap the rows. And I want to get to the block matrices stuff, so I'm just going to write down, and you can confirm that if you multiply on the right, that's going to swap the columns. For identity matrices, like the example you gave, it is assumed that it's a diagonal identity matrix unless stated otherwise. Do you mean square? I mean, the identity matrix is always the same, right? It's always the square matrix with ones on the diagonal and zeros everywhere else. So that's always square. And these elementary matrices mean generally, yeah, they're generally square. If you have, but of course you can multiply, say, matrices with more columns, for example, in a situation like this, and they'll still do the same thing, right? So if I had a 3-row but 10-column matrix and multiplied on the left by this thing, it would do exactly the same swapping of rows of that bigger matrix. Oh no, yeah. So E1 and I3 are not the same. This, I just wanted to point out that this looks like the identity matrix with the bottom 2 rows swapped. And it is the identity matrix with the bottom 2 rows swapped. And if you multiply another matrix by the identity matrix with the bottom 2 rows swapped, it's going to give you that matrix with the bottom 2 rows swapped. So that's the point. And these matrices are performing what we call elementary row operations, which are things that are going to come up for us in a couple of weeks. Okay, so give you a second if you have any questions, either unmute or type them in. Could you guys hear what my son asked me for? Okay, good. He's 7. Yeah. Yeah, I know. I'm gonna leave you that way. No chance. You'll wish that you didn't know if I told you, and you won't be able to forget it. Yeah, so now block matrices. So I wanted to walk through this, one of the activities from the textbook, because somebody asked about it on the discussion, and I think it's a good one. And if you've already listened to the video and oh good, if you've already listened to the video and stuff, then then seeing it again, it's always you know, you learn it at another level a second time. And the other thing I wanted to do was go through this exercise from the additional exercises in the text. I think this is also a fun one to do. So, oh, no, it's not. I'm sorry. Let's see. Let's see. Okay, so let's go through this one then. So we have these two matrices A and B, and the idea is that they are comprised of submatrices, these little blocks, and and bits of them are identity matrices. Right? So I2 is 1, 0, 0, 1. And if we want to find the product of A and B, right, we could, if we wanted to, fill these things in. So A11 is 2 minus 1, 5 minus 4, 1, 0, 0, 1. And then let's see, 2, 2 was minus 4, minus 3, minus 3 and 2. And then this is another copy of the identity matrix, 1, 0, 0, 1. Right? Everybody see where this is coming from? Right? Like this is, stop me if you don't. Right? So this is A11, this is A22, that's the identity matrix, and that's again the identity matrix. So we could write this out. We could write B out like that too, and try to multiply them together. And then we're multiplying a 4x4 matrix with this other thing, which is, you know, computationally tedious, and I don't want to do it. So the way I'm going to do it is by using these block matrices, especially because I'm noticing here, right, that there's identity matrices. And if there's identity matrices, that means there's a whole bunch of work that you don't have to do. All right, so let me write these down in their block form. So we've got A11, I2, I2, and A22. And then we've got I2, B21, and that's it. All right, so this is, you just, you know, when you're doing this with the blocks, you just pretend they're regular old entries. This is a 2x2, and this is a 2x1. The resulting matrix is going to be 2x1. And what are we going to get? Well, it takes a little to write out, but it's not that bad. So we'll have A11 times I2, and then I2 times B21. So A11 times I2, that's these two, and I2 times B21. The question get cut off? Do you mean this? Oh, yeah, so it just asks to enter in for those 8 different values what the value is. So like the questions for the rest of this are, what's A, what's B, what's C, what's D? It's just find product. I think inelegantly implemented, but it's your guys' job in the future to figure out how to make it better. I1 is not 0, 0, 0. I1 is the identity matrix. So this is the matrix. When you multiply it by something, it doesn't change it. We'll work it out. We'll work it out. All right, so, but maybe I should just circle this. So where this is coming from is using the top row and then this single column. And it's like taking those two things as vectors and taking their dot product. We just, when you do this kind of multiplying out, we're just pretending that these things are entries. All right, so if I do the bottom row, which is just a single entry, remember this is a 2x1, 2 rows, 1 column. Oh, so Annalisa, I don't know if maybe you didn't notice this is over here. I2 is the identity matrix. Okay. All right, so I2 times I2 plus A22 B21. So that's this second entry. I'm just taking this row and this only column and doing the, well, it's like taking a dot product to 2 vectors. Okay, so now let's sort some of this out. So when we multiply by I2, nothing changes. So that means that we're here, this A11 plus I2, there's no real matrix product to take there. If we recognize this is the identity matrix, this just, it's like, you know, if you had 7 times 1, it's just 7, right? So we just have A11 left here. And over here, I2 times B21, I2, again, it's just like multiplying by 1, except for matrices. This is just, oops, sorry, B21. So now instead of doing a whole bunch of multiplications here and a whole bunch of multiplications here, all we have to do is add, right? That's what we're left with. And down here, I have I2 times I2. That is just I2, right? 1 times 1 is 1. And then I still have to add this. I do have to actually do some work, right? We have to do one product of 2 matrices, but it's not too bad. And multiplying 2 2x2 matrices, which is what these two things are. Let's see, it was A22 and B21, right? Multiplying 2 2x2 matrices is a lot less exhausting than multiplying 2 4x4 matrices, right? Because 2 cubed is 8, 4 cubed is whatever that is, 2 to the something. Okay, so now we can work this out. We just need to find A11 plus B21. That's easy. Matrix addition is super easy, right? So this is, I'll probably make a mistake now that I said that. But 2 plus negative 1, that's 1. Minus 1 plus 1 is 0. 5 plus 5 is 10. And minus 4 plus 4 is 0. So that's going to end up being our top of our resultant matrix. And the other part we have to do I2 plus A22 B21. All right, so I'll tell you the mistake that I'm going to make here is I'm going to compute this product, and that takes thinking. And I'm going to write that down and say that that's the answer, but it's not, because I have to add ones to the diagonal. Right? Don't forget. To add the ones on the diagonal. Right, so if we multiply this out, so this is I2 plus, if I multiply this out, A22 times B21. So coming over here, so I don't have to recopy, I've got 4 minus 15, that's negative 11. And negative 4 minus 12, which is negative 16. And oh, I'm glad you like it. Yeah, I think it's super nice, right? It's a really nice trick, the block matrices thing. Sorry, I'm just responding to a comment I just saw. All right, so I2 plus, oh, right, that's what we were doing. So A22 and B21. So now we've got 3 plus 10. So that's 13. And then the last one is negative 3 plus 8. So that's 5. And this time I'm going to remember, I did this exercise in the book and I couldn't figure out why I kept getting it wrong. But it's because I didn't add the ones on the diagonal, because this is matrix is really 1, 0, 0, 1, right? So this is going to be negative 10. That'll be 6, negative 16, and 13. All right, so putting this all together, the kind of end answer, let me move this out of the way. I guess that's. The answer that we end with is really this, right? So A times B is, let's see, we have on the top this part, right? So the top of this matrix is going to be 1, 0, 10, 0. And the bottom of the matrix is coming from the product of those other blocks. The bottom of the matrix is minus 10, minus 16, 13, and 6. Okay, and the dimensions check out. If you go back and think about the dimensions of A was 4 by 4. The dimensions of B was 4 by 2. And the resultant matrix that we got here is 4 by 2, so that all checks out. So questions, anybody? Hey, no problem. All right, so we still got some time. Should we do another one? Okay, let's walk through this other one then. I'll ask you to do something with block matrices on the exam, Marco. Yeah. Okay, so this one, they're actually very specific about finding this product, and they tell you to use this particular partition, 3 by 3 matrices, right? So already we know we don't have a choice. I mean, well, I guess we do have a choice, but it already suggests to us that 3 by 3 submatrices is going to be the right way to go. And it's hard to see over here because of all the, you know, because what is this, a 10 by 10 matrix? Oh no, it's 9 by 9, that's right. And this is also 9 by 9. It's kind of hard to see over here, but if you start looking carefully, I think you'll see the lighter one. You'll see that this is just really a bunch of identity matrices. Do you see that? So it's a super boring matrix, but also super interesting. So we'll see. It's a bunch of identity matrices. And this is also kind of chunked out into layers of 3 in a kind of natural way, right? And it's full of not only identity matrices, but a couple of 0 matrices, and those are the best because you can just leave everything zeros. You're not even going to end up having to add anything. So this is kind of the idea of what I had about the last problem on that assignment that you need to upload, is how I'm going to go through this. So let's see, this matrix A, let me write it this way. I mean, this is a 9 by 9 matrix. What's 9 cubed? So just a thought towards how many operations. So the regular way of multiplying requires 9 cubed ops. So 9 times 9 times 9, that's 729. And that's just, let's see, that's just multiplications. Then you still have 9 times 9 again for the number of additions as well. All right, so let's see, let's write this down as block matrix. So this is just a whole bunch of I3s, right? Does you guys see that? If you weren't watching me, I don't think I'd even write that down. And B, if I write this down, this has got, you know, some stuff in it in the first block, a zero matrix, and then an identity matrix. And now in the next one, it's got some stuff in it. Oops, 2, 1. Some stuff in it in the first block in the second row, and then it's got 2 identity matrices. And then it's got some stuff in that part, right, the lower left block, and then it's just got a zero matrix and another identity matrix. Okay, and if I go through this again, just multiplying these guys, let's see. I know that I3 times B11, right, that's just going to be B11 because multiplying by I3 is like multiplying by the matrix version of just 1. So this is going to be B11 plus B21 plus B31, but that's just the first entry. So it's B11 plus, oh, this is A times B. B11 plus B21 plus B31. But now the next one, so I'm doing now first row, second column. This is going to be 0 plus identity matrix plus 0, right? Because 1 times 1 is 1. So that's just going to be I3, right? So that's, again, that's going across here and down here is where I'm getting that entry. And then finally, the last entry in the top row is going to come from multiplying I3, I3, I3 by I3, I3, I3. So think about that, right? I3 times I3 is just I3. And then we add it to itself 3 times. Just make that thought bubble right in your head of 1001 plus 1001, right? Right, however many times you add the identity matrix to itself, you're going to get a diagonal matrix with zeros all over the place, except on the diagonal. The identity matrix to itself. So what we're really getting is just the scalar multiple of 3 times the identity matrix. Was that clear? What did I do? I did something here. Oh, I see what I did. I want this. Right, so I see. Okay, this is 2002, right? If you add 2 identity matrices, you get 2's on the diagonal. If you add 3 identity matrices, you get 3's on the diagonal, and so on. Right, so that's where we're getting this, right? It's I3, I3, I3 times I3, I3, I3. Okay. Now, for the next one, right, we're going to get that same, well, actually, look at this, right? These are both the same again. So what are we going to get? Well, we're going to take this second row and do the same thing with the columns. And then we're going to take this third row and do the same thing with these 3 columns. These are all going to be the same. So that's computing these this is all the stuff that we have to do, right? So now we have B11 plus B21 plus B31. And what is that? That's something miserable, I'm sure. Oh, no, it isn't. So it's A plus 1 minus A, P plus 2 minus P. How they tricked us. It's just 1, 2, 3. And I3, we know what that is. And 3 times I3, we also know what that is. So what we end up with is the following, right? We have 1, 2, 3, 1, 2, 3, 1, 2, 3. We have that 3 times. I don't think I can fit. Darn it. One, two, three, 1, 2, 3. Okay. And then we have the identity matrix 3 times. Oops. Yeah, I don't know who sighed just now, but I'm writing it, you know. And then we have 3 times the identity matrix. 3, 0, 0, 0, 3, 0, 0, 0, 3. All right, so you guys get the idea, I think. So let's think about, like, that was a very verbose you know, discussion here, but you can see that this required a lot less computing than actually multiplying every one of these rows and adding them all up for, you know, 9 cubed entries or 9 squared entries, and then each of the entries requires 2 times 9 operations, right? So let's see, what did we have to do here? Well, we had to sort out this stuff. I mean, basically think about multiplying out a 3 by 3 matrix. So that's 27 operations, kind of. And then we had to do 3 additions. So let's see. Actually, let's just count the numeric multiplications here. So this didn't require any multiplications. This doesn't require any multiplications. This required was just filling in the diagonal with 3s. I mean, we saved a lot of computation, right? There's no multiplications that happened in this particular example. If you want, you could think of 3 squared times 2 additions here, right? Because each one of these matrices has 3 squared entries, and then we're adding twice. So that's 3 squared entries and 2 additions each time. So that's 18 additions. And I3 didn't require any multiplications at all. And this doesn't require any multiplications or additions really at all, right? It's just filling in 3 entries. So 18 operations versus 729 operations is a big savings. Okay. Okay, so I think we're just about out of time. We're past time. Sorry, I kept you. You can watch the video at a higher speed later on, and then it won't be as long. Does anybody have questions about anything? I have office hours tomorrow, and on Wednesday. I've forgotten the times now, but there's already Zoom meetings set up. So you can find them there. And again, I know a lot of people signed in after I said this, but the issues with the zybook assignment deadlines are being resolved. There was a time zone issue. zybook doesn't account for the time zones. So I have to set your assignment due times to be like 3 o'clock in the morning on East Coast time. But you can just ignore any kind of alerts or, complaints that zybook is giving you. I'll still be able to see everything that you do. So just do it and pay attention to the Canvas deadlines. Let's see. Yeah, I think that's it for me. Any questions? Otherwise, we're going to sign off in a sec. Okay. Bye. Have a nice day. You too, Vigor. I hope your weather is as good as it is here. Man, it's 70 degrees and sunny. All right, bye.